Good morning, students. Welcome back to another session of data structures. In this session, I will be starting Unit 3, and this is stacks and queues. First, I will be starting the concepts of stacks, and in this Unit 3, this is my chapter 2, and chapter 1 is queues, and I will be discussing it later, and this is my class 17. So, in this session, I will be mainly concentrating on the concepts of stacks. First, be familiar with the concepts of stacks, and after that, I will be discussing about the queues and queue concepts. Okay. Now in this PPT, I will be explaining you the following concepts, that is the introduction to stacks, the representation of stacks in memory, that is array representation and linked list representation, and all the operations on stacks. Okay. Coming to the introduction to stacks, I will be discussing you about what is a stack and how it will be and everything. Okay, now coming to stack. A stack is a linear data structures. Till now we have seen many linear data structures, that is arrays, linked list, and this is another data structure which is a linear data structure, that is stores the elements in a sequential order. Linear means nothing but storing all the elements in a sequential order. And in this linear data structures we have four types, that is arrays, linked list, stacks and queues. Okay. In this stack, the operations are performed from one end, that is top. That is the insertion and deletion operations in a stack are performed from the top of the stack. And insertion operation, that is insertion of an element into a stack, is called push, and deletion of an element from the stack is known as pop. So in a stack we can perform two operations, that is pushing an element into a stack and popping an element into a stack, that is inserting an element and deleting an element. Here if you observe, you can see in the diagram that we are pushing the elements and popping the elements from the top of the stack only, and we are also having a pointer called top which shows the status of the stack, that is how much up to which level or up to what level the stack is full. Okay. And push is an operation to insert an element and pop is an operation to delete an element. And here in the next figure, if you see a stack with 5 elements, and we have inserted the elements from the top, and we will also delete the elements from the top only. Okay. In a stack it follows last in first out procedure. What is last in first out? That is the element that is inserted at the last, that is the element that is inserted at the last will be deleted first. Okay, so it is also known as last in first out. Okay, in short we will say one thing: a stack is a linear data structure. The insertion and deletion operation takes place at one end only, and insertion operation is called push, deletion is called pop, and it follows last in first out procedure. Next, in a stack only two operations are allowed, that is push the item into a stack and pop the item out of the stack. A stack is a limited access data structures. Elements can be added and removed from the stack only at the top. As I have told you, in a stack we will be inserting an element and deleting an element from the top of the stack only. Okay. from one end only, the insertion operation and the deletion operation will take place. Push adds an item to the top of the stack, and pop removes the item from the top. Okay. To add an element into a stack, we will the operation is known as push, and to delete an element from a stack, the operation is known as pop. In either cases, either pushing or popping, we will do from one end only, that is insert on the top only. A helpful anthology is to think of the stacks of books. You can remove only the top book, also you can add a new book on the top. This is an example for a stack, that is I am placing the books one on a shelf. I will be placing one after the other in an order, and I will be removing it only in the same order. This is an example for a stack. Other examples of stack are also available, that is placing of cardboards on a cargo van. If I want to load cardboards in a cargo van, I will be loading them in a order, and after that I will be removing them also from one end only, that is the last cardboard placed in the cargo will be removed first. So loading and unloading of cardboards in a cargo van also comes under the example of a stack. And other example of a stack can be when we go to a restaurant, we will be ordering some items, and the waiter there or the server will place all the items in his plate and bring it to our table, and then he will remove the first item, that is on the top, the item he kept on the top. First he will remove it and keep it on our table, then the next plate he will remove and keep it on our table. Like that, the last item he kept on the top will be removed first and kept on our table first. So this is also another example for a stack, that is it follows last in first out, that is the last element deleted will, that is inserted, will be deleted first. Now, a real world stack allows operations at one end only. For example, we can place or remove a card or plate from the top of the stack only. Okay. Likewise, stack ADT allows all data operations at one end only. At any given time, we can only access the top element of the stack. That is, a stack follows last in first out, that is the element that is inserted first will be deleted last. Okay. Now here is a diagram showing you the stack and its operation. Here the elements of a stack are known as data elements or items, and these items in the first figure, if you observe, they are pushing the data elements into the stack from the top side only, that is one end only. Here in the first figure we will see pushing operation, that is the data elements are inserted into the stack, and in the next figure if you observe, we will be removing the elements, that is we will be removing the data items or elements from the stack one by one from one end only, that is from the top of the stack, and this operation is shown as pop. Okay. This diagram shows you how a stack will be, and how the push operations will be done, and how the pop operations are done. Both the operations are done from the top end only, that is from one end only, insertion and deletion. That is the element that is inserted at the last will be deleted first. Okay. Now, representation of stacks. The stacks can be represented in the memory in different ways. that is by using arrays, structures, pointers and linked list. Of the all these, the main basic are the array and the linked list. That is, stacks can be either be a fixed size one, or it may have a sense of dynamic resizing. That is, stacks can be represented in the memory in two ways. That is, mainly in two ways. One using arrays, that is fixed representation. One using linked list, that is dynamic representation. Static representation using arrays, dynamic representation using linked list. Static means the size will be declared before and it cannot be resized. Dynamic means the size can be varied. When an element comes, we can insert a node and we can change the size of the linked list. When we delete an item, we can remove the node. That is, it can be resized. Linked list can be resized and it is called as a dynamic data structure, and array is called a static data structure because its size cannot be changed. So representation of stacks in memory is done mainly in two ways. One using arrays and other using linked list. Okay. Now, array representation of a stack. First, we have to allocate a memory block of sufficient size to accommodate the full capacity of the stack. Then, starting from the first location of the memory block, the item of the stack can be stored in a sequential order. For this array representation, we consider an array of fixed size, that is, assume it is 10 size. Okay, we will take the array of size, some fixed size, and store the elements of the stack in this array, and the elements are stored in the sequential order only, since it is a linear data structure. Now, here is the array representation of a stack. If you observe this diagram, you can see an array. Here is an array and a one-dimensional array. And in this array, the index shows that L is the lower bound, that is, L is the first location and U is the upper bound. And if you assume it is as 1, then L is 1, then next position will be 2, next position will be 3, so on and up to N. And the elements will be inserted from the top only. See here, the elements are being inserted into the stack, and top is a pointer which shows up to which level the elements have been inserted. Okay. Don't be confused with the diagram. If you are unable to understand it, learn it in the reverse model, that is, turn it upside down and learn it. That is, L will come to the end and you will be going up, and that is, L is the lower bound and you will be in the upper position. Then you will be inserting from the up. Here in this diagram, they have inserted from the down position. That is, since the upper bound is down, they will be inserting from the down position. So don't confuse, both the representations are correct. That is, inserting from one end only. Here also the insertion is done from one end only. Since we have written the U value down, the insertion is done from the down. Okay, and top is one of the pointer which shows the top, how up to which level or up to the what level the stack is filled. Okay, this is a representation where we have a fixed size one dimensional array. That is, we are using a one dimensional array to store a stack. Okay, this is a static representation, that is the size of the stack cannot be changed during the execution of the program. Once it is fixed, that is fixed. Okay, next, in the figure, item I denotes the ith item in the stack, and L and U denote the index range of the array in use. With this representation, the following ways can be stated. See, as I have mentioned here in this diagram, L shows you the lower bound. That is, if we assume a stack of size 10, that L will be 1 and U will be 10. Okay, and L and U shows you the size of the stack, and item 1, item 2, so on are the data or elements inserted into the array or stack. See, empty, top less than 1. If my top goes less than 1, since I have told that L is equal to, if I assume a stack of size or array of size 10, then my lower bound will be 1 and upper bound will be 10. If it is less than 1, then the stack is empty. If it is greater than 10, then the stack is full. Okay, see, top less than 1 means top less than lower bound means it is empty. Top greater than or equal to U means upper bound. If my top is greater than or equal to, that is, since I assumed a stack of size 10, if my top is less than 1, then stack is empty. If it is greater than or equal to 10, then it is full. Then I cannot insert any values. If a stack is empty, then deletion will not be possible. If a stack is full, then insertion operation will not be possible. Okay, and top is a pointer to point the position of the array up to which it is filled with items of the stack. That is, top shows you the level or the status up to which level the stack is full. Okay, now coming to the linked list representation of the stack. Although array representation of a stack is very easy and convenient, but it allows the representation of only fixed sized stack. Okay, array representation of a stack is good and easy and convenient. It is very easy. We will be assuming an array of fixed size and we will be placing the elements into that array, and it is an easy representation. But it is a fixed representation, that is, the array size will be fixed, and if we want to insert into that we will be inserting. If I want to more size, I cannot increase it. If I want to reduce the size, I cannot do it since it is a fixed size. In several applications, the size of the stack may vary during program execution. An obvious solution to this problem is to represent a stack using a linked list. So, if in general in a program I want to increase, in general applications, if you think I don't want a fixed size, I want a variable size, that is, in my application I must increase the size of the stack or decrease the size of the stack to reduce its wastage. So for that purpose I assume a linked list representation. That is, a linked list representation helps to store the stack in variable length. That is, I can change the size at runtime. This is nothing but for this linked list representation. I use a single linked list. When the elements comes into the stack, I will be adding a node into it and placing the item. If another item comes, I will be adding a new node and placing the item. Like that, I will increase the size of the single linked list. If I don't want to or delete an item, I will remove the node and return the node to the memory bank so that it is not wasted. This is nothing but the linked list representation. For this, I use a single linked list. Here is a diagrammatic representation of a linked list representation of a stack. Here, this is nothing but a linked list representation of a stack. In this, stack head is nothing but a header node. If you have uh, gone through the previous PPTs, that is linked list PPTs, I have told you that header is a node, or header is the first node in the linked list. It shows the first node in the linked list, and header does not have any data. Header only has the link part, and this link part points to the first node in the linked list. Okay. Here also stack head is a header node and it points to the first node in the linked list. Here if I want to insert an element into a linked list, I will be inserting there after the header node. That will be my top. That is the top element are the recently inserted element. That is the last inserted element will be after my header node. See, if you can observe that my top is pointing towards the item I, which shows that this is the last item in the stack. If I want to insert a new item, then I have to insert it after it. If I have to delete it also, I will be deleting the top, the element pointed by the top pointer only. Okay. This is a linked list representation. It is using a single linked list. Single linked list, as you know, contains only, the node contains only two parts. One is the data part and other is the link part. Data part stores the item that I want to store, and the link pointer will point to the next node in the linked list. Okay. The linked list representation, the first node on the list is the current item, that is the item at the top of the stack. The last node in the node linked list contains the bottommost item. Thus, a push operation will add a new node in the front, and a pop operation will remove a node from the front of the list. As I have told you, the stack header, after the stack header, the last item will be inserted. That is the item that is presently inserted, or the last inserted item will be after the header, and the first inserted item will go to the end. Okay. As you have seen, item 1 is at the end of the linked list, and item I, that is presently inserted or recently inserted, is placed after the header. Okay. Now coming to the operations on stacks. As I have mentioned, we can perform different operations on any linear or any data structures. Here are some operations that can be performed on a stack. That is push. Pushing means nothing but inserting a new element onto the stack. Okay. Pop, that is nothing but removing or deleting an element from the top of the stack. As you all know, we will be removing or inserting an element from the top only, that is from one end only, and this push operation will insert an element at the top of the stack, and the pop operation will delete the topmost element from the stack. Now, to use a stack efficiently, we need to know the status of the stack as well. For the same purpose, the following functionality is added to the stack. That is, we will push an element, that is, we can insert an element into a stack. Also, we can delete an element from a stack. Other than this, we can also perform the following operations. That is, peek. Get the top data element of the stack without removing it. If I want to know what is the data item on the top of the stack, then I use the operation peek. Okay, it gets the recently placed element on the stack. For example, consider I am having a stack, and on that stack I have inserted the. If I want to retrieve the topmost element, or if I want to know the topmost element of the stack, what element is on the top of the stack, then I use the peek operation. Is full. It checks if stack is full. If I want to insert an element, I first want to check if the stack is full or not. For this checking, I use the operation as is full. Is full is an operation which checks the stack and returns if the stack is full or not. Okay, is empty. This is another operation used to check whether the stack is empty or not. If I want to delete an element from a stack, first I must know whether the elements are there or not, or whether the stack is empty. If a stack is empty, I cannot perform the delete operation. So first I will check if the stack is empty or not. So this operation is used to check if the stack is empty or not. At all the times we maintain a pointer to the last pushed data on the stack, and this pointer always represents the top of the stack, hence named top. The top pointer provides top value of the stack without actually removing it. That is, in a stack I will also have a pointer, and this pointer will always point to the topmost element in the stack. That is, pointer top will always point to the recently inserted or the lastly inserted element or the topmost element in the stack. Now, coming to the first operation, that is push operations. The push operation, to insert an item into a stack, I need to perform the push operation. Okay, first, to push an element into a stack, I need to know the status. What is the status now? Status means nothing but whether the stack is full or whether up to which level the stack is available. For inserting any element, first I will check whether the stack is available, whether up to which level the stack is filled. The process of putting a new data element onto a stack is known as push operation. Push operation involves a series of steps. First one, you can write it as an algorithm also. These steps you can write as a descriptive algorithm for a push operation. Okay, that is nothing but the insertion operation on a stack using array. First, check if the stack is full. If the stack is full, produce an error message and exit. If the stack is not full, increment top to point next empty space. Add data elements to the stack location where top is pointing. Last step is return success. See, this algorithm explains you the procedure to insert an item or insert a new item into a stack. That is, first what we will do, we will check if the stack is full. If the stack is full, then we cannot insert any new item into the stack. Then we will just show an error message or message that stack is full. So no insertion is possible. Otherwise, if the stack is not full, then we will increment the top pointer and point it to the empty space. Then place our data on that empty space and return back. Again, I will repeat the step once again. See, if the stack is full, then we will come back. Because I cannot insert on a full stack, I will come back and show the message that is stack is full, so insertion is not possible. If the stack is not full, first I will increment the pointer and then it will point to the empty space. Now I will insert my new item in that empty space and then return success. That is, I have placed the element successfully. Okay, see, this is the push operation. Here, I have been inserting the elements into the stack. That is, here I have already inserted, I have already A, B, C, D in my stack. Okay. Now I want to insert another item, that is E. So first I will check if my stack is full. If my stack is full, I will not be able to insert and I will come back. If my stack is not full, I will place I will increment the top pointer and it will point to the empty space, and then I will place the E there, that is the element E, and then I will return back. See, here in this procedure, here in this diagram, you will be able to see a stack of size 5 and already 4 elements are filled, and now I am inserting another element E onto the top of the stack. Okay. Now, algorithm for push operation. Here is an algorithm for that is used to push an element into a stack. Begin the procedure. First, begin procedure push. That is stack comma data. First, if I want to push an item into a stack, first what I should do? If stack is full, that is, first check if stack is full. If stack is full, return null. That is, return null. That is an error message, you can say, or a message showing that stack is full, and then come back. And if means then return back. If it is not full, else if it is not full, what I should do? Increment the top, that is top is equal to top plus 1, and place the data item on that location. As I have explained you earlier, if the stack is full, then return an error message. If the stack is not full, first increment the top value and point it to the empty space. Then place the new data item on that location that is pointed by top. Here this algorithm shows the same procedure. Okay. Now, pop operation. This, as I have mentioned, this operation is used to delete an element from the top of the stack. That is, the last element on the stack will be deleted using this pop operation. As you all know, a stack follows LIFO order, last in first out. The element that has been inserted at the last will be deleted first. Okay. See, the descriptive algorithm for performing the pop operation is as follows. Step 1. Check if the stack is empty. If the stack is empty, produce an error message and exit. If the stack is not empty, access the data element at which top is pointing, and decrease the value of top by 1. Return success. This algorithm says that first, if I want to delete an item from a stack, first check the status of the stack. If the stack is empty, if the stack is empty, then I cannot perform the deletion operation on an empty stack. Then just to show that the stack is empty or underflow means the stack does not contain any items to be deleted, and then come back. If the stack contains some items, then delete the last item, that is the item pointed by the top. Delete that item and decrement the top value by 1 and return success. Okay, once again I will be telling you, see, if I want these push and pop operations are very important for your exam point of view, so mainly concentrate on them only. Okay, pop operation is nothing but you will check if the stack is empty. If the stack is empty, then we cannot perform any deletion operation, so we will just say one thing: stack is empty, so no deletion is possible. If the stack contains elements, first delete the element pointed by the top pointer, that is the topmost element will be pointed by the top, so delete that element. After deleting, decrement the top pointer by -1, that is decrement it by 1 and then come back. Okay, now here see, here I have a stack of 5 values A, B, C, D and E, and my topmost element is E, that is the element on the top of the stack. First I check if the stack is empty. Here if I check it is not empty, so I can proceed forward and see what is the topmost element pointed by the top pointer. It is E. So this element should be deleted. First delete that element and then decrement the top pointer by 1. And now see in the next figure, if you see, the second figure shows you that the element E is being deleted and the top pointer is decremented and pointing towards D. Okay, this is the pop operation or deletion operation on the stack using arrays. Next, algorithm for pop operation. A simple algorithm for pop operation. As I have explained earlier, this operation is used to delete an item from a stack. So first what I do, if stack is empty, return null. That is, first I check if the stack is empty. If the stack is empty, I return back since I cannot delete any item. If it is not empty, data stack of top is equal to data and top is equal to top minus 1. That is, delete the item pointed by the top pointer and then decrement the top pointer by 1 and return the data, that is return the data back to the memory bank, like that you can say, and end procedure. This is a simple algorithm that you will be using for performing the pop operation. This push and pop operation on stacks is very important. Practice it with the algorithms also. You can write the descriptive algorithm, also this algorithm, both. Now peak. Algorithm of peak function. Begin procedure peak. Return stack of top. That is, this peak operation returns the element on the top of the stack. If I want to know which element is on the top of the stack, then I perform the peak operation. This operation will return the topmost element without deleting it, just it will show me the topmost element. Return the stack of top, that is the topmost item on the stack. Okay, Next, is full. Algorithm for is full function. That is, if I want to check my stack is full or not, then I use the is full function. Begin procedure is full. If top equals to max size, return true, else return false. If I am having an array of size or stack of size 10 and my lower bound will be 1 and my upper bound will be 10. If my stack size is equal to 10, that is maximum size, then I say my stack is full, and else I can say my stack is not full. Okay, if my top pointer points to maximum size, then I say that the stack is full, else I can say stack is not full, and I can perform the insertion. This operation mainly checks if the stack is full or not. Now, is empty. This is another operation which checks if the stack is empty. Okay, begin procedure is empty. If top less than 1, return true, else return false. That is, if I am having a stack of size 10, my lower bound will be 1 and upper bound will be 10. If my top is less than 1, that is less than my lower bound, then I say my stack is empty. Otherwise, I can say my stack is having some space and I can perform insertion. Okay, this function is mainly checked when the insertion or deletion operation is performed. Okay, if a stack is empty, then I cannot perform the deletion operation. If a stack is full, then I cannot perform the insertion operation. Okay, hope you all understood the stack introduction, then representation of stacks in memories, that is array representation and linked list representation, and the algorithm or the operations on stack, that is push, pop, peek, is full and empty operations clearly. Okay, since these are all very important, practice them. Okay, thank you. This is the end of class 17.